Okay, in our last videos we saw how to prepare amines primarily through SN2 style chemistry. Today what we're going to look at is a slightly different method. We're going to prepare amines through something called reductive amination. I want to show you the overall idea first. And the overall idea is quite clever. The idea is first start with a ketone or an aldehyde. Works with either, so let's make a note here, ketone or aldehyde. And what we want to do is we want to first make an imine. So what we can do is react this with some sort of amine. In this case, I'm just going to use ammonia. And we're going to remove water in this process. So we saw this chemistry in our ketone and aldehyde chapter. And because it's under acidic conditions, we're going to be left with an intermediate that is protonated. So we're going to get an protonated imine, which is just called an aminium ion. And then the goal in the second step is, well, if we've made this aminium ion, can we just reduce this double bond to a single bond? So is there a way of reductive amination where we can reduce that bond into a single bond? And so this was tried, and the tricky thing was finding reductive conditions that worked well for this. And so I'll show you a part of the problem here. Part of the problem was if you try the reduction with our typical hydride sources, it'll reduce the ketone or aldehyde before you can even form your aminium ion. So let's make a note. So if you try using NaBH4 or LAH, the CO double bond gets reduced before you can form your amine. The idea with this reaction that I have shown up here is that we would like to be able to do this in one pot, meaning we don't want to have two separate reactions. We actually want both of these to occur in the same reaction vessel. That way we don't have to purify intermediates and we can just simplify the overall procedure and improve yields. So what they had to do was they had to investigate reductive techniques that were a little bit more gentle, one where it wouldn't react with the CO double bond, but would react with the CN double bond in the aminium ion. So let's take a look at our various hydride sources. So we'll make a list of our strongest H- source, and that would be LAH. And if you think about what lithium aluminum hydride is, we've got aluminum with 4 hydrogens on it, and the aluminum has a negative charge. All right, next up, we know that sodium borohydride is weaker. And in this case, we just swap out the boron for the aluminum. And this is going to be a lot weaker hydride source, primarily due to the atomic size of boron, right? It's smaller, so those hydrides are held more tightly to that boron, versus aluminum, being a very large atom relative to boron, is going to be more willing to give up one of those H minuses. All right, so we're going down to our weaker H minus source, and the one they found that works quite well is sodium cyano borohydride. Actually, normally it's written NaBH3CN. So what this looks like is NaBH4, but instead of a 4th hydrogen, you're going to have a nitrile. And what this does is it really slows down the reactivity and makes it more manageable. So let's make a note. So it makes the negative more stable due to electronegativity. And if this entire reagent is more stable, that means it's going to be less reactive, meaning it's going to be less likely to react with the CO double bond. However, it's just reactive enough to react with the CN double bond in the aminium ion. So the way I like to describe it to people is it's kind of this Goldilocks effect. We want a reagent that will react here, but will not react here. So we need something that's powerful enough to do the reduction, but not so powerful enough that it actually reduces our starting material first. All right, there are other hydride sources beyond sodium cyanoborohydride that can be used for reductive amination, but this is the one that they primarily use in our textbook, so we're going to stick with that. All right, so let's take a look at how this would work in our example problem that we previously looked at. So in our example problem, we had our generic ketone or aldehyde at the top of our notes, and we can do this all in one pot. So we just say, all right, we need acid, we need our amine source, so this will form our aminium ion, and then in the same reaction vessel, we'll throw in our sodium cyanoborohydride, and we can completely replace our CO double bond with a bond to our nitrogen. And in this case, the nitrogen right here is just adding in right there. So it's a really easy technique. It's one that's used commonly in the pharmaceutical industry because it's so versatile and it can be used to make some of these synthetic alkaloids quite easily. All right, so let's take a look at why they like using this. And it's primarily because this reaction is versatile. All right, so let's take a look at all the different things we can do with it. So the first one is we can make a primary amine. And like I said, we can make this using the technique shown above, where we just use ammonia as our amine source, and we use sodium cyanoborohydride. And if we do this, we get a primary amine. So that's pretty useful. However, we saw that we can make primary amines using the Gabriel synthesis and other methods like this. This allows us, however, to make primary amines that otherwise wouldn't be easy to make, because if you think about doing SN2 chemistry here, if we try to do SN2 chemistry to get that carbon-nitrogen bond, that's fairly hindered. So this allows us to get to fairly hindered primary amines. All right. Furthermore, we can have acid, and we can react it with a primary amine as a reagent, and then treat it with the same reducing agent, sodium cyanoborohydride. And if we do this, we can actually make an amine that is now a secondary amine. This is something we couldn't do with our SN2 chemistry before. So this is definitely an improvement over previous chemistry. And then last but not least, you can probably imagine where this is going. You can react this with a secondary amine. So I'll call this HNR2 prime, and we'll react this with sodium cyanoborohydride. If you think about the reactivity during this first step, well, you're going to still make an aminium ion, but we're not going to go all the way to our enamine because it's quickly going to be reacted with the sodium cyanoborohydride, and we're going to reduce the aminium ion. But this allows us to make tertiary amines. So it's a combination of chemistry that we've seen in our aldehyde and ketone chapters, along with a new reduction technique. It is a pretty popular technique to use. There are other techniques available as well that aren't covered in our textbook, but for all intents and purposes, this is our Swiss Army knife, meaning our most powerful tool for making any amine we want in the textbook. So this is one of the most important reactions, in my opinion, in this chapter. All right, so let's take a look at an example. All right, this example I think is pretty interesting because it's actually used in the pharmaceutical industry to make a very popular drug. But the intermediate, before I tell you what the drug is, looks like this. So they're able to build this intermediate. And then what they need to do is they need to do reductive amination on the CO double bond, and they need to get a methylamine on there. So what they're going to do is react this with methylamine and catalytic acid and that sodium cyanoborohydride. And when they do this, they're going to completely change that CO double bond to a carbon-nitrogen single bond. And then everything else in the ring is going to stay put. This prevents over-alkylation. It's a nice, easy reaction to perform. It can be scaled up. And this is how they make the drug Zoloft. Now you might be thinking, okay, we do have a stereocenter here, and it is important to note that when they do this synthesis, they're going to get a racemic mixture, meaning they're going to get both R and S at that stereocenter. But this is commonly used within the pharmaceutical industry. All right, so now let's take a look at a more complicated practice problem. All right, so let's try this one, and we're going to do the opposite. We're going to give a target and figure out what we need to make it. Okay, and my target in this case is going to look like this. It's going to be a bicyclic ring system where the nitrogen is actually one of our bridgeheads. Let me clean this up a little bit. And we need to figure out how to make this. Well, there's a few different approaches we could use. What I like to do is first identify all of the carbon-nitrogen bonds, right? Because up here, we saw when we did this reaction, our goal was to make, let me change colors here, this carbon-nitrogen single bond. So if I look down here, I've got a carbon-nitrogen single bond right here, got a carbon-nitrogen single bond right here, and I've got a carbon-nitrogen single bond there. So maybe we made one of these bonds. So what I would say is let's just pick one of them. So for example, I would say, what if we created this one? Okay, what would the starting material have to look like if we wanted this yellow bond to be made? And in fact, I'm going to just erase those to make sure that it's super clear. All right, well, let's break this apart. Well, if that bond were made, then the nitrogen would have had to have been on its own, right? So the starting material, let me even back up further. The starting material would have had to have had a nitrogen like this, right? And then over here, on this side, we must have had a CO double bond, right? So in this case, this is a good example of an intramolecular reaction. If you want to show that aldehyde hydrogen, you can too, but in this case it's kind of crowded, so I might even just leave it out here. So if we wanted to do this, you can see that the amine is actually built into the molecule. This amine right here will react with the aldehyde that's kind of in the tail, and we can form our aminium ion. So all we need to accomplish this reaction is to treat this with a small amount of acid and then our sodium cyanoborohydride. If you want to draw this out so that it looks a little bit better, you could. Oh, that doesn't really make it look a lot better. Let me draw this nitrogen more clearly. So we've got over here 1, 2, 3 carbons. So I'll go ahead, say 1, 2, 3. And then the last one is our aldehyde. This would be a good starting material. Okay, so this is a pretty nice way of forming these intramolecular bicyclic rings as well. Okay, there are a ton of problems in the textbook that are quite helpful, so I would recommend going through as many practice problems as possible. See if you can deconstruct a lot of these. I'm not going to do a ton of practice problems here, but we can maybe do an impromptu Zoom study session to go over some of these practice problems from the book if you would like. Good luck studying.